Hello, my name is Lawrence Bloom, and today we're going to look at the derivation of the Black-Scholes model using the Cox-Ross-Rubinstein-Model. So what we're going to first look at is the theory and the model, and we will algebraically derive if the Cox-Ross-Rubinstein model converges to the Black-Scholes model. Then we're going to use our knowledge to price a barrier option utilizing a Monte Carlo simulation and a Cox-Ross-Rubinstein model, and then I will give a quick overview of my appendix. So let's dive straight into it. The Cox-Ross-Rubinstein model is actually based on rather plain basis. So what we have here is a binomial tree with two states, an upward state and a downward state, and the usual payoff of a call option here. And what we do now is we try to replicate the cash flow of the option. So we try to get the upward state of the call option and the downward state, and we do this by having n1 parts of S0 and n2 parts of risk-free capital. And as you can see here, we apply the law of one price. So now we take n1 times S0 and 1, as you can see, with small t being equal to 0, and get the price of the option. And as you can see here, it's just the discounted probability weight call upward state and downward state. And we can take this to the next level, to a more general level, by introducing n steps. So for example, here we have 4 steps, j upward moves. For example, here we have, in this terminal node, we have 0 upward moves, maturity t, and length of a period capital T divided by n. And we also introduce continuous discounting. So what we have right here is the continuous discounting part. You have the probability of an upward move to the power of j, which are upward moves. We have the payoff of the call option, and we have the binomial coefficient. So what does the binomial coefficient do? The binomial coefficient determines how many different unique ways there are to reach a terminal node. So for example, this node down here has one unique way to get there, and this is this one right here. But for example, this one has multiple ways. So now we can apply a little bit of algebra, show two convergences and so on, and do like 3 pages of algebra, and then we can get that for the number of steps going against infinity, we can see that the discrete Cox-Ross-Rubinstein model converges against the Black-Scholes model, and we actually get exactly to the Black-Scholes model. And we can also show this in a model. So I have done a Visual Basic model to show this. On the x-axis you have the number of steps in the tree, and on the y-axis you have the percentage deviation to the Black-Scholes model. And as you can see, the Cox-Ross-Rubinstein model converges with an increasing number of steps in the tree, and it does so in oscillating fashion. So oscillating means we have this waveform in here. So as you can see, for an odd number of steps it's always above the price, and for an even number of steps it's below a price. And this is not random. This is because, as you can see here, just from in a binomial tree with n steps, with an even number of steps like here, you have a 0 in there. And this is caused by u being equal to d to the power of -1, which is why we always underprice the option with an even number of steps in the tree. So let's apply this knowledge to price a barrier option. So first of all, what's a barrier option? A barrier option is an exotic option that can be knocked in or knocked out. And in the following, we will just look at a call European option which can be knocked out. And I think I can best show this in a graph. So let's say you have 10 paths of a stock, and this one up here is your knockout. And let's say this blue graph or green graph here actually breaches the barrier. It's no longer relevant for us. It extinguishes, and it's knocked out. This is why we can use a Monte Carlo simulation to generate a lot of paths to price the option. And we do this by utilizing the geometric Brownian motion that you can see here. And for example, here you have 100 iterations, so you generate 100 paths and see which one crosses the knockout and which one don't. And the relevant ones for us are the ones which are not out, obviously. And you can do this for 10,000 iterations, for 100,000 iterations, and so on. And the most important question is, does it actually converge to the Black-Scholes price of a barrier option? And yes, it does. As you can see here, the orange line is 10 to the power of 4 iterations times x. So at this point right here, where x is equal to 100, you have 10 to the power of 6 iterations, And you can see that for an increasing number of iterations, we get closer to the Black-Scholes price of the barrier option. So what's interesting now is to see if the Cox-Ross-Rubinstein model, which is a discrete model, also works on a barrier option. And the problem here really is that it's discrete and that it's non-continuous. So we have a problem with our binomial coefficient, because if you think about this terminal node right here, there are a couple of ways to get there, which the binomial coefficient determines, but there is also a path which gets knocked out, which is this one right up here, because it reaches the barrier, and we would have to subtract this. And you need to solve this combinational problem for n steps, so you can't just subtract all the paths that you see. And once you've done this, and I've done this, you can write in the model just to see the deviation to the Black-Scholes price for an increasing number of steps in the tree and plot this, which is exactly what I've done here. And as you can see, we converge to the price, but we do this in a sawtooth pattern. By that I mean, first of all, we got this right here, this effect here, which is very equal to the oscillating function, and it's also caused by the odd-even effect, so odd number of steps was even number of steps. But we also have those huge jumps in here, which is caused by periodic ringing, which, well, let's say you have an increasing number of steps, then your tree changes the position relatively to the strike price, which is why we have the periodic ringing. So it's just to give you a quick overview of the appendix. This is what a front end looks like for my model for pricing a plain vanilla option using Cox-Ross-Rubinstein. Here you have option matrix, and here you have the number of steps. And here you have the back end, so really the code. And I've also included Python code to show you how to generate multiple paths using Monte Carlo, utilizing the geometric Brownian motion. Thank you very much.